Hi all. So let's solve this question. In this question, two predicates are given to you, Pn, Qn. These are predicates. Open statement. Open statement means predicate. So remember, this is another name for predicate. So you can call it predicate or you can call it open statement. So two open statements are given to you, means two predicates are given to you. Pn means n is odd, Qn means n square is odd. The universe is a set of all integers. This is the domain. Now the question is saying, which of the following statements are logically equivalent to each other? Some statements are given to you. We need to find out which of them are logically equivalent to each other. So let's write all of them in first order logic. Let's translate all these statements into predicate logic. So let's see this first one. The first one is saying, if the square of an integer is odd, then the integer is odd. We are saying, if the square of integer is odd, then integer is odd. First of all, you tell me, in this statement, are we talking about all integers or we are talking about some integer? Means this statement A, is this existential statement or is this universal statement? In this statement, do we have universal quantification or do we have existential quantification? So think about it. This statement A, this is saying, if the square of an integer is odd, then integer is odd. Are we talking about all the integers? Are we saying for all the integers, are we saying that if the square is odd, then integer is odd? Or are we saying for some integer? Means this statement A, this is universally quantified statement or is this existentially quantified statement? You think about it. Okay. So let me tell you, this is universally quantified statement. In this statement, basically we are saying if the square of an integer is odd, means for all integers we are saying, that if the square is odd, then that integer is also odd. So this type of statement, these are universally quantified statement. Now you will be thinking, sir, where it is given? In this statement A, where it is given that it is universally quantified statement? In this statement, we don't know. You might be thinking, you are thinking that is this existentially quantified or is this universally quantified? How do we know? So let me tell you very simple. In this type of statements, the universal quantification is implicit, means that is hidden. Universal quantification is hidden. Okay, so many times universal quantification will be hidden. See this statement, read this statement and this statement will automatically tell you that this is universally quantified statement. This is saying if the square of an integer is odd, then the integer is odd. So this is talking about all the integers. For every integer we are saying that if the square is odd, then that integer is also odd. So in this statement, universal quantification is hidden. See, many times in the real life also, we make statements, we speak some statements in which universal quantification is hidden. For example, you see this statement. So in your real life, sometimes you have spoken this statement, politicians are bad. This statement you have spoken in your real life. So in this statement, do you mean by all politicians? When you speak this statement, what do you mean? So it simply means, you simply mean that all politicians are bad. So you can notice here universal quantification is hidden. In your real life, you have spoken this statement, natural numbers are integers. Okay, this statement is true, natural numbers are integers. But in this statement, are we talking about all the natural numbers? Are we saying that all natural numbers are integers or are we saying that some natural number is integer? What are we saying? This statement, does it have universal quantification or does it have existential quantification? The answer is this has universal quantification. Here universal quantification is hidden. Okay, basically we are saying that for all natural numbers, they are integers. Here we are saying for all politicians, they are bad. And what about this statement? This is your favorite, sin square theta plus cos square theta equal to 1. In this statement, are we talking about some theta or are we talking about all theta? See, this is your favorite equation from your school life. This is the favorite equation. You know that sin square theta plus cos square theta equal to 1. But my question is, are we saying for all theta or are we saying for some theta? Is this universally quantified statement or is this existentially quantified statement? So you know we are saying for all the angles theta. So here you can notice we are basically saying that for all angles theta, you can notice sine square theta plus cos square theta will be equal to 1. So you can notice this is hidden. For all angles theta, this was hidden. So this was hidden, right? This is what I am saying, that in all the statements, here you can notice for all natural numbers, this is hidden. For all natural numbers, this was hidden, or I can say this was implicit. You can either call it implicit or you can call it hidden. So you can call it implicit. Means when you say that sine square theta plus cos square theta equal to 1, here you are saying that for all angles theta, whatever value of theta you put, this sine square theta plus cos square theta will always be equal to 1. So you can notice when you speak this equation, whenever you are saying this equation, then it is hidden that it works for all the angles. It is hidden. It is implicit that it will work for all the angles. So this for all theta, this is hidden. So final conclusion that universal quantification is many times that is hidden. Okay. In many statements that we make this statement, we make this statement, we speak this statement. In many statements that we speak, universal quantification is implicit or universal quantification is hidden. Now let's come back to our statement A. So in this statement A, we are saying that if the square of integer is odd, then integer is odd. Here we are saying for all integers we are saying, okay, this is hidden. For all integers we are saying, for all integers x we are saying that if x square is odd, then x is odd. So remember here, you can say for all integers x, this is actually implicit, or I can say you can either call it hidden or you can call it implicit. I told you that many times universal quantification is hidden. So this is your statement A. So what is statement A? I can say statement A is for all integers x you are saying the domain is already set of integers. You can see the domain is already set of integers. So we are saying for all integers we are saying that if x square is odd, then x is odd. So for all integers, for all x, the domain is set of integers. So for all integers we are saying if x square is odd, then x is odd. X square is odd, that means qx. So I can simply say that is qx, implies x is odd, that is nothing but px. X is odd means px, x square is odd means qx. So I can say this is statement A. This is for all x, qx implies px. This is your statement A. Now let's see the statement B. Statement B is saying for all n, Pn is necessary for Qn. So first of all, what is Pn is necessary for Qn? How to write this? Pn is necessary for Qn, that means Qn implies Pn, right? See these two statements. One is A is necessary for B. So this how do we write? We write it as B implies A. A is necessary for B. This is how we convert this into propositional logic, that is B implies A. A is sufficient for B. We write this as A implies B. So you can see what is your option B? The statement B. The statement B is for all n, Pn is necessary for Qn. Pn is necessary for Qn means Qn implies Pn. So your option B is basically for all n, Qn implies Pn. Now remember one thing, that this x is just a bounded variable. You can replace this x with n also, no problem. This x, this is a bounded variable. So you can rename it. So you can simply call it, for example, you can simply call it n. So what I can do, instead of this x, I can simply use n, no problem. For example, I can say this statement A, this statement is for all integers n. For all integers n, if n square is odd, then n is odd. This is your statement A. Okay, for all integers we are saying if n square is odd, then n is odd. So for all n I am saying Qn implies Pn, right? So this is your option A, this is your option B. You can notice they are equivalent. So here you can easily notice that statement A is equivalent to statement B. And the question is asking which of them are equivalent. You can notice which of the following statements are equivalent. So you can notice these two statements, they are equivalent to each other. What about statement C? Now see the statement C. In this statement C we are saying the square of an odd integer is odd. So again you can notice here universal quantification is hidden. See, read this statement carefully and tell me, is this universally quantified statement or is this existentially quantified statement? Are we talking about some integer or are we talking about all the integers? So you can see this statement, the square of an odd integer is odd. In this type of statement, you can notice universal quantification is hidden. We are talking about all the integers. For every integer you are saying, For every integer n, you are saying that the square will be odd. Okay, for every integer you are saying that if it is odd, then its square will be odd. So remember, in this statement option C, the universal quantification is hidden. Again, we are talking about all the integers. We are saying for all the integers n, if it is odd, then its square is also odd. So this is your statement C. We are saying the square of an odd integer is odd. Means for all integers we are saying that if it is odd, then its square will be odd. So read this statement carefully. The square of an odd integer is odd. Means for all integers n, we are saying that if it is odd, then its square will be odd. So very simple. Again, you can notice this is hidden for all integers n. This was implicit. You can call it implicit or you can call it hidden. I told you that most of the time, many times, universal quantification is hidden. Okay, in our real life also, many times we speak statements in which universal quantification is hidden. So very simple. For all integers n, we are saying if n is odd, then n square is odd. N is odd, that is nothing but Pn. N square is odd, that is nothing but Qn. You can notice n is odd means Pn and n square is odd means Qn. So finally, this is your option C. Option C is for all integers, for all n. The domain is set of integers, remember. So I can say for all integers means for all n, if Pn implies Qn. Now you can easily notice this is your option C. But what is option A, option B? Option A, option B, statement A, B. Statement A, B are for all n, Qn implies Pn. So these are statement A, B. I told you. So from here you can easily notice that this statement A was equivalent to statement B and they are not equivalent to statement C. So this statement A is not equivalent to statement C. Similarly, statement B is not equivalent to statement C. So remember, A, B are equivalent because statement A, statement B, they are saying for all n, Qn implies Pn. But statement C is saying for all n, Pn implies Qn. So this statement and this statement, they are not equivalent. P implies Q is not equivalent to Q implies P. So I can say this statement C is not equivalent to statement A, statement C is not equivalent to statement B, and statement A, B are equivalent. Now see option D, statement D. Statement D is saying there are some integers whose square are integer. There are some integers. So this is existentially quantified statement. We are saying there are some integers whose squares are integers. So you can notice the option D. This is basically saying that for some integer. This is saying that for some integer. Remember, for some integer n, we are basically saying there is some integer n whose square is odd. Means there is some integer n such that n square is odd. So how to write this statement D? This statement D you can simply write like this. We can say that for some integer, the domain is also set of integers. You can see the domain is also the set of integers. So what I can do, I can write this as there exists integer. There exists integer, because remember the domain is also set of integer. So I can say there exists integer. So I can say there exists integer such that n square is odd. That means Qn. That means Qn. So I can say there exists n such that Qn. So very simple. Okay, so you can write like this. There exists n such that Qn. So you can again notice that this option D, this is not at all equivalent to option C. This option D is not equivalent to option A, because option C is saying, what option C was saying? This was saying for all n, we are saying that in option C we are saying that Pn implies Qn. This was your option C. And option A was for all n, Qn implies Pn. This was your option A. So now you can notice that option D is saying there exists some integer such that its square is odd. For some integer n, its square is odd. So I can say there exists n such that Qn. Now this is definitely not equivalent to C. This D is not equivalent to A. Now let's see the next statement, that is statement E. Statement E is saying that given an integer whose square is odd, that integer is odd. Okay, so you can notice. Now here again you can notice, read the statement carefully, think about it. What this statement is saying. Is this talking about some integer or is this talking about all integers? Is this existentially quantified statement or is this universally quantified statement? Think about it. We are saying given an integer whose square is odd. Okay, given an integer means any integer given whose square is odd, then that integer is odd. So here we are talking about all the integers. We are basically saying that given any integer whose square is odd, given any integer, I give you any integer whose square is odd, I give you any integer whose square is odd, then that integer is odd. So very simple. Here basically we are talking about all the integers. We are saying given any integer whose square is odd, then that integer will be odd. Okay, so here remember we are saying given any integer whose square is odd, that integer will be odd. We are basically saying that for all integers and we are saying that if the square is odd, if n square is odd, then that integer will be odd, means then n will be odd. So here what we are saying that for all integers we are saying if n square is odd means qn, n is odd, that means pn. So I can say for all n we are saying that if qn happens, then pn happens. If qn happens, then pn happens, and that is same as your option A. So option E, this option E, I can say that is equivalent to option A, that is equivalent to option B. Okay, very simple. Also option A is not equivalent to option C. Also you can notice option C is not equivalent to option D, and option A is not equivalent to option D. Okay, so this is the idea. So far we have seen these statements. So far we have seen that option E is equivalent to option A, that is equivalent to option B, because you can see option E is saying that for all integers, if its square is odd, then that integer is odd. For all n we are saying if qn, then pn. So far we got this, that these two statements A, B, these are equivalent to option E. Okay, and so you can see. Now let's see option F. What this option F is saying, statement F, this is saying for all n, negation px implies, see, I think this is pn. Okay, so there is a small mistake here. So I think this is a pn. So in this option F, what we are saying for all n, negation pn implies negation qn. So this F, this is saying for all n we are saying, for all integers we are saying that negation pn implies negation qn. Now this you already know that we already know that any conditional statement, negation p implies negation q, this is equivalent to q implies p, because any conditional statement, this is a conditional statement, this is equivalent to its contrapositive. What is the contrapositive of negation p implies negation q? That will be q implies p. So here I can say that option F is for all n, qn implies pn. Okay, and that is same as your option A, that is same as option A, that is same as option B, that is same as option E. So this is your option F. What is the next option? That is option G, statement G. Statement G is saying for all n, pn is sufficient for qn. First of all, pn is sufficient for qn. What that means? That means pn implies qn. So here I can say your option G, that is saying that for all n, pn implies qn, and that is equivalent to your option C. Okay, that is equivalent to the option C. So this is the idea. So let me give you the final conclusion, that statement A is equivalent to statement B, that is equivalent to statement E, and that is equivalent to statement F. So these are equivalent to each other, and we have seen that statement G is equivalent to statement C. So these are equivalent to each other. Okay, and remaining statements we have seen. Statement D is not equivalent to any of them. Okay, statement D is separate, so I can say you can keep it separate, because statement D, that is not equivalent to any of them. So very easily you can see this. Okay, so this is your final answer. So if you have any doubt, you can ask your doubts in the comments. So whatever doubt you have, put your doubt in the comments. I will answer it. I will reply to your doubt. So don't worry, every doubt will be answered in the comment. So don't keep any doubt, put your doubt in the comments. I will answer it. I will reply to it. Okay, and let me know how many of you got it correct. Okay, did you get this answer correct? Is this the answer you got? What is the mistake you made? So let me know in the comments.